It's I'm probably one of the few people in the audience who's old enough to remember at the movies with Cisco and Ebert. Right, okay. They also did sneak previews, so that's kind of what this is. And I'll talk about work that I've been doing with my group and ex-members of my group and CK. But Nick Conroy, who used to be here, is now a graduate student, and he's been a leader on this. And then my postdoc, Nikki Balbach, has been also involved in this. So here it is. This is the product of 5 or 6 or 10 years of effort. So we have 2 nice pictures, and the question is what comes next? And I think that this, we're all attached to these results, and it's remarkable that across 3 orders of magnitude and mass, the black holes are still orange. So, okay, so what's next? Well, I was looking around the web, and I came across the NGEHT science traceability matrix, and you'll see down here that there is a goal of measuring the rotation curve of Sagittarius A star and M87. And I think this is, not required science, but it's aspirational science for NGEHT. So what do we expect to see in the way of a rotation curve based on the existing simulations? Okay, well, what we do is simulation. So I'm going to show you a state-of-the-art simulation that we did recently. So this is Uni Primary School in Urbana, and we filmed this from a drone. And there's a black hole in the middle, and you can see the plasma. It's almost collisionless. They're all running at about the same rate, so it's a flat rotation curve. Yeah, but every once in a while, someone accretes onto the black hole. Anyway, and then at the very end, I don't have this piece of the video. We talking about rated. The teachers loved that. The kids were all tired. They could go in and concentrate. And actually, we took questions from them, and one of the kids, I think this is a 4th grader, said, "No, we showed some movies there," and the kid said, "Is this an actual observation, or is this just a simulation?" Wow. Okay, so we do state-of-the-art simulations. Here's GRMHD World Headquarters. So here's our movies of M87 and Sagittarius A star, and we're interested in signatures of rotation in the movies. And you can see in Sag A star, things rotate very quickly. And in M87, this is an actual movie. They're moving very, very slowly. And so the question is, what can we measure about this? And it looks pretty easy based on this movie to track the motion of individual features in the, run that again, in the simulation. Here, you can see things moving around or moving rather slowly over here. So what can we actually measure? Well, if you convolve this to sort of nominal 20 microarcsecond resolution, then it's maybe a little bit more challenging to see what's going on. So you see an oscillating blob on the right. And if we had a longer movie, you'd see an oscillating blob on the left too. Okay, so the challenge here is to measure something that relates to rotation from this movie and not the earlier one. Okay, so the plan here.
Sorry, why does the Sag move faster? What's the story?
It's a smaller black hole, so it's 1,000. The characteristic time scale for Sag A star is 1,000 times smaller than for M87. Yeah. That has been the challenge. Okay, so the modest goal here, so sort of modest proposal, is to measure dominant pattern speed in the data. And we're going to call this the pattern frequency omega p, and this is the notation I'm going to use throughout the talk. These are going to be these are going to track the angular movement of the brightest features, the brightest fluctuations in the image. Okay, so what are our priors? What do we expect the pattern frequency to be? So, on the one hand, you might expect that it would be something related to the rotation frequency at the ISCO. In a hotspot model, that's what one produces, depending on the parameters of the hotspot model. Or you might expect to see something related to the rotation frequency of the plasma itself. So you can go into the simulations and measure the orbital frequency of the plasma. And that tends to be somewhat in the terminology that's used in astrophysics, sub-Keplerian. So I was having an exchange with Steve Balbus about this, and Steve said, well, Kepler left the scene some time ago here. So, but the Keplerian generally refers to the frequency of circular orbits in the equatorial plane. Okay, so what does the ISCO rotation frequency look like? So this is a function, of course, of the spin parameter of the black hole. And it's expressed here in the units that I'm going to be using in this talk, which are degrees per m. So degrees per gm over c cubed, which is, of course, about 20 seconds for Sagittarius A star and about 9 hours for M87. And in these units, the ISCO frequency varies from something like 2 degrees per m to something like 14 degrees per m over the range and spin that we typically consider in EHT simulations, which run from minus 0.9375 to plus 0.9375. Okay, so does this work? So let me put up a movie here. And I have a clock hand that's going to show the rotation frequency of the ISCO on top of a simulation. So let's let this run. So this is a spin 0.5 model. So the ISCO rotation frequency is more like 7 or 8 degrees per m. And you can see that, there are some features here that actually do seem to move close to the ISCO frequency. And there are others that are much, much slower, especially these large scale features here, which actually contain most of the brightness of the image. Yeah.
What would be the diameter of the ISCO on that image?
Where does the ISCO? Well, it's somewhere around here. It's, yeah. I mean, I haven't done that exercise of taking ISCO in the equatorial plane and projecting it onto this onto the image plane.
It's roughly the size of the photon ring.
Yeah, it's a little bit bigger than the photon ring, I think. But to be clear, in the simulations, the ISCO doesn't really. There's no marker at the ISCO. Plasma just flows in across the ISCO. Innermost stable circular orbit. Yeah. Okay, so this looks a little bit fast for what we expect, and from the movie, and this shows the expected rotation rate from the simulation. So these are time and azimuth averaged rotation frequencies. Okay, so this is. To be specific, this is there's no chalkboard here. But you would need a working marker to be able to do this. So this is omega is u phi over ut. And this is a coordinate dependent quantity. So the circular orbits have the same u phi over ut in Kerr-Schild coordinates, which is what we commonly use in simulation, and in Boyer-Lindquist coordinates. But if you have an orbit with radial velocity, then the two differ. Okay, so it matters whether it's Kerr-Schild or Boyer-Lindquist. In any event, this shows the rotation frequency expected for a set of models. The same models are up here, and these are on near Keplerian orbits. So if you want to know where the circular orbits in the Kerr metric are, they're just almost right on top of these lines. These are a little bit super Keplerian in places and a little bit sub-Keplerian in others. And then, of course, the MAD models are substantially sub-Keplerian. Okay, so whichever way it goes, you can see in this region where most of the emission comes from, say between 3 and 4M, that the orbital frequency is something like 2, 3, 4, 5 degrees per M in the MAD models, and maybe a little bit more like 8 degrees per M in the same models. Okay. So, so then we need to go, actually, maybe we can, thanks. We need to go and measure this pattern frequency. And there's a little bit of a process here, which is an idealized process compared to what we're going to be able to do with the data. So in some sense, this represents, you know, an aspiration for the data, even from NGEHT. You know, we're talking about a simulation where we have thousands of time samples and perfect resolution, and no, you know, UV sampling artifacts or the like. Okay, I think we're going to, Daniel has been talking with us about how to actually do this calculation of real data. So we start in each image with identifying where the photon ring is. And, you know, we have an approximate analytic expression for this. And this overplots the approximate analytic expression, which is the expansion in the spin parameter. And it really lies right on top of the photon ring. So it does a really good job. And then we blur this image to nominal resolution. So this is the resolution that one would expect at 230 gigahertz with a full, you know, with the full diameter of the Earth. And what we're going to do is measure the brightness temperature, T brightness, on this circle. And I can say later if people are interested in what happens if you move the sampling radius around a little bit. But you know, the width of this is a fair fraction of the ring width. And so it turns out to be relatively insensitive to exactly where we put the ring down or how we select the ring or that sort of thing. Okay, so from this.
And the center of the ring as well, the choice of center will make a difference.
Yeah, so as long as you can get it within a beam width, it doesn't really matter. Okay, so what we do is sample on that ring and extract the brightness temperature as a function of position angle and time. And, you know, just to go back here, in this particular model, the brightness peak is over here on the left. Position angle 0 is up here at the top. So we expect the brightest point on this diagram to be at position angle of 90 degrees. And then to have a dimmest at 270 degrees. Okay, so this is a sample simulation. This happens to be a MAD model with spin 0.5 and so on. And you can see time on this axis and position angle on this axis. So again, the top of the ring at noon is up here. The bright spot is over here. Oh, it turns out I can actually mark on the screen. And then the dimmest part is up here at 270 degrees.
You've been here for so many years, we never knew this.
Okay, so we're interested in measuring fluctuations on the ring, and if we just decompose this, what we're going to see is the bright spot and the dim spot, and that's all we'll be able to measure. So what we do is take at each angle the average and then subtract it. So we're looking at fluctuations in the brightness versus position angle rather than the brightness itself. And so if we do that, we get something that looks like this. Okay, so this is, I think this is the kind of thing where you develop internal language to describe this. This is what we call a cylinder plot, because it's a cylinder, with time on the long axis and position angle going around. And you can see that there's a definite sense of rotation on here. These features are tilted a little bit. And if you look at the tilt, it's a little hard to identify here exactly what the tilt is. You want to plot up, some comparator line, which I haven't done. But you can see it's sort of, it goes a few hundred M in time over 360 degrees. Okay, so the time scale for this is sort of degree, or the rate for this is sort of degree per M kind of thing. Okay, so we filtered. We've tried various filtering techniques. It doesn't seem to matter all that much exactly what we do. And then we take an autocorrelation function on the cylinder plot. And this gives a very clear sense of the slope of this, which I'll get to in a second after I answer Razi's question.
Yeah, exactly. That's super fascinating. Can you please go to the previous slide? There is kind of like flux action suppression from earlier to later time. I wonder if you were doing time dependent actually M unit fixing, such that when you go to larger and larger time, and see you had you re-rescale, re-normalize the M unit. Could that be just that all of these actually, otherwise suppressed flux could get back to higher values? Or
yeah, so I think there's couple questions there. One about the variability, and as we know, the simulations have a well-known problem with variability, which is that they're too variable in comparison to the data. But I don't think that's going to suppress all of any sort of normalization scheme which acts over timescales of hundreds or thousands of them is going to suppress these fluctuations which occur over much shorter timescales of hundreds of them. So the typical timescale fluctuations, which I doubt is wrong, is hundreds of them.
okay, so how do you interpret having bright left and actually? I guess that if you were renormalize this locally for every 1,000 of M, those that are otherwise not that bright, they get back to be bright.
Yeah, so this is 5,000 M. We've used a single mass unit normalization for this whole thing. And if we tilted this a little bit, it would weight the data slightly differently. I don't think that's going to change things dramatically for the measurement that I'm going to discuss.
Okay.
And here, there's a real event in this MAD model where there's a big flux ejection event, and that suppresses the brightness here.
Nice.
Okay, so we take an autocorrelation function for these fluctuations. They're mean zero, and what I've done here is plot up the ISCO slope on here. So that's, for this model, it's about 6 degrees per M, and again, time on this axis and position angle on this axis, and the tilt here basically measures the pattern frequency. And you can see that the tilt differs significantly from ISCO. So the procedure here is to first do this calculation, which I don't think we're going to be able to do with real data. I think what's much more likely to happen with real data is that we'll do correlations between pairs of images and then look at the the sort of phase delay for high M in M-ring fits. This is what Daniel was suggesting during his visit a few weeks ago. And then we'll get some distribution of those phase delays, and there'll be a peak, and that will be our peak. That will be our pattern frequency.
Is there, am I missing something? Is there a reason why the autocorrelation function is their confocal ellipses? Is that telling you that there is already telling you that there is no d omega PDR?
There is the omega p dr, and in fact, the ellipse orientation changes as you change delta t. So, but not by much. And it varies actually from model to model. But you know, this is a very idealized circumstance. So we're going to look at the main signal first, and then we can worry about, you know, changes in the orientation with delta t. Yeah.
So you don't think we can measure the autocorrelation at least time, or at least something about the spectrum,
Well,
even with an M-ring fit, you can cook up models.
yeah, maybe you could do that. There's a lot of things to deal with. I don't think we're going to have regularly spaced data.
Doesn't matter.
Okay.
You can do this without regularly spaced data. You can do it. You might have to assume something about the model, whether it's Markovian, but you can do this with non-regularly spaced data. Put off a spectral estimate.
Yeah. So I
Or at
think
least I
that's
think you can. I shouldn't emphasize. I think you can, but yeah.
well. So we would need multiple images separated by of order, you know, 50 M or so in time, 20, 40, 50 M. So I think this speaks to the cadence, or is useful for thinking about the cadence of future observational campaigns. Yeah.
So Charles, this figure that we're looking at, is it at one fixed radius or is it an average over the whole image?
So we smeared the image,
Yeah.
and then we sampled at the photon ring.
Just
we
at
knew-
the photon.
Just at the photon ring.
Okay.
So this is where most of the brightness is. And I can show you later on what happens if we move off the photon ring. But, you know, not to conceal anything, things slow down a little bit as you go out. Got it. Surprise.
Okay.
So if you want a little bit of substructure, is it important to its like use?
Oh, this stuff?
Yeah.
I think
the
that's-
photon,
Yeah, I think that's a,
photon,
oh, down here. I think that's a plotting artifact. It may also be at very low levels, there's sampling noise. So there's sort of cosmic variance in these things. Out here, it's not clear that you can
Isn't
rely.
it visual because I mean, maybe
this.
on the screen it seems like there is a spot which gets dark and then bright. Get dark.
So
It looks like
in
a
here,
bit of variation, yeah, it might be just. Screen.
yeah, no, yeah, so there's striping here, which is not real. Okay, that's either this projector or a graduate student artifact. I think it's the projector, actually. So Nick is very careful.
I think he's
Yeah.
talking about the blob. There seems to be like a blob on the bottom.
This blob here and here.
Thanks.
Oh, okay. So that is actually there. That's not a plotting or a graduate student artifact. And it's just a low level feature in the correlation function. So I think I don't believe this is real. I mean, I believe that there's a feature there. I just don't believe we've measured it accurately with only 5,000 M of data. Yeah. Is that? Okay.
And there should be a feature from the secondary image.
There should be a feature, you mean going the other way?
The brightness here will have a correlation with the secondary image of the same bit of plasma, right? And it'll be a small delta T and the PA close to 180. And maybe that's
Yeah, I think that's just very faint compared to the signals that are easy to measure. I could, I'm not sure I have a full. Yeah, this is a linear autocorrelation function. Yeah, it's, I mean, we tried to see if we could find other pattern frequencies in the data, which is related to this last point, which is that to test our procedure, we made a Gaussian random field realization of this cylinder plot with a known frequency. And then we were able to extract that. So that was helpful and confirmed, helpful in building our confidence in this. We also built Gaussian random field models with multiple frequencies, and you really just tend to see the brightest features. Yeah. So that's one message here, is that it's really hard to dig out the faint features that one might expect to see, like the secondary image. Okay, so now that we have a technique that perhaps you believe for this, we ran it across the whole simulation library. So our Sag star simulation library, and we measured the pattern frequency by, again, putting a line down on this and evaluating the slope of the peak, basically. And for this model, the slope is about 1 degree per m. Okay, so this is 30 degrees, which in this business qualifies as nearly face on. And again, mad, so this is kind of what we think might be going on in Sagittarius A star and M87. Spin 0.5 and large values of R high. Okay, so first point to make is that the pattern frequency that we see is slow. Okay, so it is not what you would expect to see from hotspot models. So the measured value is down here at about 1 degree per m. And the plasma rotation frequency is up here about 5 times higher. So we're seeing something else. We're actually seeing, I think we're seeing a pattern frequency. We're seeing shocks that are propagating in from further out in the disk and moving backwards along the flow. And these things move relatively slowly. Okay, so that's point 1. And
So, Charles, before you proceed, we have this autocorrelation function with a slope. I'm not able to visualize. Is there a bias in the presence of noise? Does noise only decrease the signal, or does it actually bias the slope?
That's an interesting question. Yeah, I don't know. Okay.
Something tells me that there might be some effect, but yeah.
So are you concerned that this slope is too low and that it's biased by noise in the simulation?
That's the question. Yeah, that's the question.
Yeah, I think that's possible. I have a list of caveats later, and it's on there. So in particular, most of the variability in the models may be due to these features, these spiral features. And we know that the variability is too large. So these spiral shocks may be the problem, and they may be de-emphasized in future simulations, which you know, are hyper resolved, or which are include additional physics that like diffusive physics that reduces the variability.
Yeah, so regarding to Ramesh's question, can you do like 3 actually time windows, and in each of them separately compute the slope, and then just, you know, just compute the median actually and the errors?
Yes, we've done that, yeah.
Oh, okay. Is any two?
So there's a little bit of noise actually. So amazingly, even with 3 5,000 M windows, which would be a long time for Sagittarius A star. I mean, Michael would have significant gray hair by then.
Or no hair.
Yeah, for him himself, or no hair if they're for Sagittarius A star, it would be less time, of course.
Yeah.
But even with those 5,000 windows, we see sort of 10%, 15% fluctuations in the slope.
And a follow-up question, if you switch to non-thermal electrons, is the same
So we haven't-
changes? Oh, I see. Okay, would you expect them to be faster or slower or somewhat similar?
Well, I'm going to answer your question later when I get to what happens when we run this over the whole library. Okay, but before we go to this, let me just put up the clock hand here and look at what happens to the smooth simulations when we run this around. And we had versions of this that look better and versions that look worse. So this is pretty typical. And you can see that there are some features that sort of move with that clock hand, and then there was one that moved really quickly. Yeah. So that might be an interesting thing to pursue, is these fast moving features. It might be possible to see this, but there you go. So there's a large bright feature which shifts sort of with the characteristic frequency. And that's what's easy to measure here. Okay, so this is not an observation, so we can go back and uncover what's going on under the hood and see what happens when we deblur this simulation. And you can see that the clock hand is really following these large scale features, which contain a significant fraction of the non-axis metric brightness. And there was the guy running around there. So there are some things that move faster, some things that move slower. But what we've, I think, done is measure the dominant pattern frequency in the image. Okay. So, so what happens when we fit across the whole library? And this will answer your question, I think. For the pattern frequency as a function of our usual 4 parameters, which are the spin of the black hole, the inclination of these aligned models. So all the models that we fit to are aligned in the sense that the angular momentum of the accretion flow is aligned or anti-aligned with the black hole spin. And we've also included dependence on whether the flow is sane, low magnetic field strength, or MAD, high magnetic field strength. And then we've also run over models with different values of this R-high parameter, which is our way of encapsulating a lot of physics related to the electron distribution function. And what we see here is very similar results for the pattern frequency for both MAD models and sane models. So they all go at about 1.1 degrees per amp.
So when you look at it directly based on there's no pattern frequency, if I hear that correctly?
No,
sorry,
it's edge on.
Edge on, yeah.
Yeah, so if you look at the movies and the edge on guys, you see things coming this way, and there's no net sense of rotation. So in that case, you know, had we the resolution, it would be interesting to track features close to, you know, you're in the bright spot, moving toward the equatorial plane, if either Sagittarius star or M87 were edge on. And we think they're not. Okay, so this is most sensitive to the inclination. So we see nothing when it's edge on, and we see the full pattern speed when it's face on. So I think that's interesting. That may not be the sort of sexy result that everybody wants from this, but it's an important parameter in the modeling. And if we could nail down the inclination, it would be extremely helpful. It is also somewhat sensitive to the spin, although less sensitive to spin for the MAD models than for the same models.
Any dependencies on the black hole mass?
Well, it's going to scale with the black hole mass. You know, all else held constant, flux held constant, optical depth held constant. Yeah. So it's here. Yeah, see, it's degrees per amp.
So this is a sine spin.
This is signed, yeah. Yeah, so if we flip it over, it goes the other way. And so one of the key points is that we would be able to check which way, say, Sagittarius star is spinning. And for example, does it go in the same direction as the spot seen by the Gensel group, as the infrared bright spots, and is inferred from the QU loops in the infrared.
So I may be misremembering because you and I have chatted about this at length, but
Or I may have put something on.
no, I recall retrograde models not having the pattern speed go in the direction that I expected. So do you see it dominated by the black hole angular momentum or by the disk angular momentum?
Disk. It's a disk.
Okay.
We're seeing the disk.
Yeah.
And then small contribution from the hole. So if it's retrograde, this is a signed quantity.
Yeah, exactly. So even if that's like 0.94 or minus 0.94.
Or minus 0.9.
Yeah, exactly. You're still done.
So if it's retrograde, it seems to spin a little bit more slowly.
Right. So just for other people who worry about this kind of thing, this is tremendously surprising to me because you could have a retrograde high spin mad with a knockout 180 and you still see the disk dominate the pattern speed. That is fantastic.
Is that right? Sorry, I'm trying to understand the sign conventions. This is always the same sign. If prograde to retrograde, you flip the sign of A. So it's saying it slows down, but it's still going the same direction on the star.
Correct.
So it's set by the black hole spin. It's not that.
No, it's set by the accretion flow. So the inclination here refers to the orientation of the accretion flow, angular momentum vector.
Oh, I see.
Yeah.
Okay. That is surprising.
It's it's good to ask why it's surprising. And I think one reason why it's surprising is because we know that, for example, in the M87 models, the bright side follows the spin of the black hole rather than the angular momentum vector accretion flow.
As does the beta 2 phase. So this is a distinct feature, and this I think is the clearest evidence that this is a shock and not you're not watching individual parcels move around. Very cool.
Yeah, I agree.
Another question, is it degrees, meaning 360 in the circle, or it's radians?
This is degrees per m.
So it's like degrees 360, just
Yeah.
like.
Yes, correct. Yes, correct.
So are you going to explain where the 1.1 comes from? Or
Yeah. The honest answer is we don't fully understand this. It's some kind of average over all of the rotating features in the accretion flow. But one thing that we have done is go and look at movies where we mask out everything except the emission in a particular latitude bin. And these features that are driving the pattern frequency are close to the midplane. Typically, so they're not. Yeah.
I have a speculation
Yes.
that this guy is really a frequency tied to the initial torus,
It could be.
right? And so it's a pure, artifact of the way you set up the simulation.
It could be, although we have different pressure maxima for the same models and MAD models. So they differ by about a factor of two.
Okay,
And
you
they
get
give
the
the
same frequency.
same frequency. Yeah. But one thing I worried about was that these are some kind of sort of jet disk interface kind of features, and they're not that. So I think it's really, shocks driven from a little bit out in the flow. If you work this back to Keplerian orbital frequency, you can assign a radius to it, and that's about 20 out.
That's what I was thinking.
Yeah.
It kind of is where you started with torus.
Yeah, absolutely.
Good.
So
I've got a couple of simulations
Yeah.
where I put the pressure maximum at 500.
And I want to know what pattern speed is.
I don't know
Yeah.
because I don't know how to do these calculations, but yeah, we should look at it.
Yeah.
Long simulations,
Yes.
pressure maximum inner edge is all way out. And we can see whether it gives the same answer.
So I'm going to make a prediction.
Yes, it'll be
It's
1.1
going to be
degrees.
1.1.
So you'll kill my speculation. Okay.
But, there are some caveats here. Yeah.
So I would expect that for the retrogrades, if you chose a much smaller radius, that the features would follow the black hole spin, probably in only the unblurred version because it's a lot fainter there. Have you seen that?
So we have gone to the smaller radius and they're a little bit faster, but not a lot faster. So these spiral shocks actually penetrate into the region inside the photon ring.
Mhm.
And so, as we know, the inner disk edge is inside the photon ring. And so they go all the way in.
But I mean, the sense of rotation, does it flip at some radius?
That we've not seen that. It seems to be the same.
Yeah, actually, it's a follow-up to Andrew's question. Maybe you can find where the emission come from and fix that actual calculations to that location. Would you expect to see some differences or even more similar actually pattern?
So we haven't got a complete exploration of that, but again, we've looked at different latitudes to check that it's not jet disk interface that's producing this. Yeah, and we do kind of know that it's, most of the emission comes from 3, 4, 5, right?
I think that could be interesting to come up with some semi-analytical understanding of the parameters that contribute into omega p. And then if you have them using some Raya for other action models, then that could be much easier to make a map between, different types of simulations, the spins and other parameters.
Yeah, so I think that would be interesting. I mean, it kind of makes sense if you think about spiral density wave theory here. You have an inward propagating wave that's propagating against the spin. It's moderately tightly wound, so that increases the pattern frequency or decreases it in this case. And so it kind of hangs together in that sense. Okay, so this is my sort of credo here. Underselling our theory, so I have to tell you about all the holes in this, or at least some of the holes. And so here are the limitations. So one limitation is that we've used fast light approximation. And if there's any measurement for which fast light should be suspect, it's this one, where things are moving on the dynamical timescale at sort of 3 or 4 M. And we're fortunate to have at least one model that we've imaged at very high cadence in fast light and slow light. And in that model, we still see the same pattern speed independent of cadence, but we see a slight increase in the slow light model, where we actually propagate the light through the simulation at different times. Okay, so that makes some difference here. That may increase the pattern frequencies a little bit. Cadence is limited to 5 GM over C cubed. So, you might expect that if we have very high cadence, which is observationally achievable, at least for M87, then we might see some of these fast moving features more easily. But that does not appear to be the dominant measurable feature in the numerical data. Okay, so 3 is what we worry about a lot. And that's the point that I mentioned earlier, that the models are known to be too variable. And we may be looking at the pattern frequency of the feature that is in fact too variable. So we may be looking at the pattern speed of the excess variability. Another concern is that a lot of the signal comes from the faint side of the ring, which may be more challenging to measure. And hopefully with next generation HT, we're going to be able to measure a larger dynamic range, and that will be okay. And finally, the actual measurement is likely challenging. I don't think this is going to use exactly the same technique that I've described here. So with, maybe Paul will rescue this. But I think it's more likely that we will look at phases of components in the Emory models and look at how the phases evolve in time. Okay, so I am about done. So I want to summarize some things here. So what we've done is, do autocorrelation function of the brightness temperature on this ring, which is on the photon ring, and use that to measure a pattern speed. And we validated this against a Gaussian random field model where we know what the pattern frequency is. And the headline here is that the pattern frequency is unexpectedly slow. So it's 1 degree per m, which is a prediction for future measurements. That when we do this with NGHT, we're going to see spiral waves and not hotspots running around at the geodesic frequencies. So if we look at this pattern speed over the entire simulation library, we find it depends mainly on inclination. So it's a way of measuring inclination. And then more weakly on spin. And then it's insensitive to whether it's mad or sane. And this is the first time this has happened in our whole, business of looking at these models. It's insensitive to the electron distribution function model, which I think answers your question, Roxy, earlier. Of course, we haven't tried non-thermal models, but we've run over R high from 1 to 160, which is a pretty dramatic change.
If I may something actually, in our beta 2 paper together, we also figure out that when we go from the normal to the Faraday thick models, R high is not too important, but that was because fundamental properties like the magnetic geometry velocity. Yeah, so no, I'm just saying that maybe omega p is could be really written in terms of those fundamental quantities that are not sensitive to R high.
So even if we can't measure omega p, it ought to be possible to at least measure the sense of rotation, which I think is interesting for comparison with the Gensel case, or actually Gensel results with gravity. And
Which are at much larger scale.
those are at about 10 M now. And they, it's very hard for me to make sense of those measurements because it's not the orbital frequency at 10 M. But there's a sense of rotation that comes from that. And it's clockwise on the sky, which is the opposite of what I showed in all the movies. And so that suggests inclination greater than 90 degrees. So we can check that out. And then finally, I'm not sure we have a full theory of this. I think it's interesting to look at. But our best bet is that they're associated with these features are associated with ingoing waves. Okay, I think I've got all of those.
Is that disk associated?
That they are disk associated, yes. Yeah. And in fact, it gets really complicated when you look at individual models, the ones with the greatest variance around that fit are the same models with large R high. And those guys have more of the emission on the jet disk interface than on the midplane. Okay, so that's it. And I have the final dolly.
I was, one of the things that we struggled with in the imaging paper for the Sedgwick Star was these jumps, or apparent jumps in the movies that we were experimenting with. And one thing we found was that when closure quantity is crossed zero change sign, we got these jumps when we were doing test simulations. Another was that some of the variability was in these unsampled zones in the UV coverage. But I think it's very interesting what you showed here, where the spiral arms, because they're rotating different rates, sort of cross or overlap one another as a function of radius of an angle, and then you can get these quick moving hits to the center of brightness. So I thought that was a really interesting lesson, and is important for us thinking about these things going forward as we deal with real data as well.
I was curious about the M87 correlation image that you showed earlier. Was the position angle what was the simulation to rotate, or was the spin axis oriented like vertically?
So first of all, I only showed Sagittarius star
Sorry.
models, but
Sorry.
so I just didn't want anyone to. So the similar thing happens in base models. Yeah, so the spin axis was pointing slightly up in the image toward position angle 0. And so the material is circulating around like this, and the bright spot is on the left-hand side of the image.
So I didn't hear the response about the blobs. Is it talk? So I'm not sure if this question is, maybe you already know the answer to this, but are the blobs somehow related to the position of the spin axis? Or is that?
Oh, you mean if we rotated it like this? So this measurement is going to be invariant under rotation of the spin axis on this guy. So it doesn't matter. We don't have to get that right. On the other hand, all these models that I've looked at assume that it's an aligned or anti-aligned flow. So the angular momentum vector, accretion flow is parallel or anti-parallel to the black hole spin.
Yeah, so this 1.1 degrees per m, and I know you mentioned you looked at several different radii. This is just the photon ring radius, right? The other thing that you mentioned very briefly. So that's
okay,
a single radius measurement.
so let me
yeah, so here's a radius dependence.
so this is a tilted model, so the numbers are a little bit lower. Here's the photon ring here. So this is 0.75. Yeah, it's higher if you go in or if you go out.
Yeah, so actually what I was hoping to ask about is that that's not the only thing that matters for this measurement. It's also the time scale across which you're measuring the slope in these autocorrelation plots. So you mentioned that is not necessarily just one slope there. So where are you pinning your measurement of the slope in these autocorrelations, or is it kind of fluctuated in some?
Yeah, it's basically autocorrelation function weighted.
Yeah, so that's what I mean. This intensity in that plot weighted.
Yeah.
Okay.
There are lots of ways of doing this, and they all get the same answer. So you can look for the peak in the autocorrelation function along different delta position angles, or you can take a second moment of the correlation function, or yada yada yada.
Yeah, I'm thinking of even like the elliptical contours and their orientation as you move out.
They do change a little bit.
Yeah.
But this, I'm glad to get the chance to go to my backup slides.
So they ask.
So this shows fast light and slow light, but it also shows the effect of time resolution. So we have a fast light and a slow light with 0.5 degrees per m sampling. And these give pretty similar numbers for the pattern frequency in this model, which is tilted at 60 degrees. So cosine of the inclination appears there as a half.
Right, so this is the resolution of the sampling, but that's somewhat distinct from you have an autocorrelation that's extending over many tens or hundreds of m in like full width half max in time, right?
Yes.
Like the peak of this function is distributed, and that is what I expect to change.
Well, so there's a correlation time, which is pretty brief. So if you look, let me go back to this. So this here is kind of a correlation time for the fluctuating component. And you can see it's about 25 m.
Right, but even in this plot, like the green line that you're showing looks like it's misaligned with what I would call the elliptical contour interior to certain.
Yeah, this one, yeah. So
and maybe more aligned with the outer ones. So that's the sort of S shape or whatever it's going to be.
This is a weighted measurement.
Yeah.
Yeah, so there's a little bit of S-ness here.
But that looks like it could be substantial. It looks like it could be a factor of 2 in the slope almost. Is it something that's really, this 1.1 number is somehow very anchored to a particular time scale?
No, it's again, it's a weighted average of the time scales. So we've weighted it according to the autocorrelation function, which is a measurement of how confident we are in the measurement.
Yeah, so continuing with Dom's question. have you looked at the real long duration simulation and seen whether this thing wanders with time?
Well, so we haven't done that. We have a few 60,000 simulations now.
You're welcome to use my 100,000. I've even got a 250,000 if you want.
Well, we've got a lot of work to do. I mean, we're also interested in looking at Sean's wrestler sort of self-consistent simulations. We have those sitting there. We don't have them.
Okay, but you don't see any hint with what you've looked at of time evolution of this? Or
Not yet. So we've looked at 10 to 20, 20 to 30,
Okay,
and 30 to 40, and that doesn't really change anything. Yeah.
Are you hopeful for there being signatures just in visibility amplitudes? I thought I remember on some call at some point you could see the sense of rotation in them.
Yeah, you can definitely see that if you look at maps of the visibility, and you can see the rotation. And what happens there is an interesting question. So first pass was to look at this in image domain, but it's interesting to ask what happens in movies. I don't have an answer.
I guess comment to the question. Comment is, NGHT is targeting, the rule of thumb is an observation every 3 days for 3 months. So that is, a few hundred M with pretty regular cadence. So I actually think this is a pretty conservative prediction. I mean, I think you could basically do exactly the procedure you've outlined. And then the question is, have you done this for the EHT observations of M87? Because there, we see the brightness slide by tens of degrees. Let's call it 90 degrees. So it's actually 5 degrees
in the wrong direction.
in the wrong direction, which makes it even more exciting.
Yeah, so you gotta keep in mind that, so that would be astonishing. That would mean that it was a retrograde system, I think. That would be
Well, so it means that the brightness asymmetry is coming from.
yeah, so omega P goes with this, and the brightness asymmetry goes with the spin of the black hole. So it goes with it. But you only have like a week's worth of data, which is not that many out.
But it definitely moved.
It definitely,
Yeah, you take off the mean here though, right? It's part of Charles's estimate, takes off the mean image, you will have no estimate for the mean image off 3 days of data.
Or and more than this, watch the bright spot. See, it's gonna go. Okay, now it goes that way,
Yeah.
right? So maybe that's what.
so we have many
You
years.
expected it to bounce around.
Many years to estimate the mean. Also, you could take a Matrix-L historical data sample and you could get an estimate and then have a big error bar, that'd be great. But I think actually doing exactly the procedure you described, the data we have in hand is not so far off.
There's no other question, Charles. A more general thing, and I think right up your alley. People have been looking at spiral galaxies, right? And there's a whole theory on what is the pattern speed of the spirals, and there's the Lindblad resonance and the co-rotation resonance, and all that nonsense.
Yeah.
How much of that might actually be relevant or might translate to our problem?
Yeah, people have even done that for black hole tests, of course.
Okay, yeah. QP also.
Michael Novak's thesis stuff.
Mhm.
Yeah, so these are shocks, so they're not necessarily going to behave exactly like linear waves, but we know what the dispersion relation is for linear waves. So it's something like this. Okay, so this is the orbital frequency, and this is the pattern frequency, which is the same as what I've defined here. And this is the M number here. And this is the cyclic frequency, which in the emission region is about 0. Okay.
Really? Kappa is.
Yeah, close
this
to
is
the
the
ISO.
maximum and just.
It's small.
Okay, right,
Yeah.
okay.
So it's just this. It's just a sound wave, rotation modified. And so that tells you, so you can solve this for omega P. Let's see if I can do this on the fly. I'm not sure. So this tells us that omega P is equal to omega plus and minus CSK over M, I think. And so, when you're going against the flow, for large values of K, for example, you can produce a feature that's almost stationary. Now, exactly what K is here, it's sort of like 1 over R, right? These are not very tightly wound density waves, which is the regime fluidity for this. So anyway, but it's quite possible that this gives you a pattern speed that's close to 0, right? Much smaller than this.
But the way these patterns form and adjust, I think they adjust K, right, as a function of radius. You just change your angle of the spiral in order to satisfy this. But it still leaves the question of what determines omega p, right? Where is it located?
Yeah. So I think it's
Somewhere
feature center
far
a
away.
little bit
Yeah.
far out, and that really makes you worry about relaxation. So that's I'm interested in seeing what the long term
Yeah.
relationship is.
Yeah.
I mean, for the spiral galaxy case, I think omega p as a function of R is something that's calculated, right? If you assume that you know the origin of the density.
Yeah, so I think they have co-rotation very
Co-rotation,
far
yeah.
out, so maybe 10 kiloparsecs, multiple scale lengths. If it's unbarred.
Unbarred.
That's the
by-
thing. Because unless
Bar.
it's the bar
That's the end of the Laura's.
So omega itself is a function of radius as well.
Yeah, this is.
Could that
the-
be that they cancel out each other? Because I think that you were suggesting that omega p shouldn't too much matter in terms of where you are.
Okay, well, if it's just a feature that's embedded in the disk, so there's no propagation sound speed, propagation speed is 0, then it's just omega p is equal to omega. So those are the bright spots that are affected with flow, right? And then this thing allows you to cancel out some of that because you have a backward propagating shock, and backward propagating shock allows you to reach a small omega p. This is a lot of guesswork.
But there are also 2 solutions, so it could be either faster or slower. Which one could happen in reality?
plus minus.
Oh yeah, well, so if you're inside co-rotation, then it's going backwards. Yeah. So one comment on the shock business is that these bright features are shocks in a collisionless fluid with electron temperature that's relativistic and ion temperature that's non-relativistic. And I think those shocks are really under-theorized. I mean, people talk about dissipation from House or Kawazura, dissipation at the bottom of an alphane cascade, as if that were the only dissipation present, when a lot of the dissipation may be in these shocks, in these collisional shocks. And I've been working on trying to figure out what people know about that, and the answer is not a lot, I think.
Yeah, we have a final question from Maciek. Then we should probably release our speaker for today. Maciek.
Hi, Charles, can you hear me?
Yeah, we can hear you.
All right. So I made this calculation in the chat, and you discussed a little bit application to M87 data. In M87 in 2017, there was a shift of 30 degrees in 5 days counterclockwise, which gives you 2.25 degree per M. And I didn't see your equations, but I think it means that dimensionless spin must be 5.
The dimensionless
What do you think of it?
5?
Well, I understand
But
it,
Maciek,
assuming med.
but Maciek, you're not necessarily looking at a smooth evolution that's related to one of these spiral shocks. You only know that if you have a lot of data over a long period of time. Otherwise, you may be seeing one shock crop up behind another.
Okay, so
And-
you do not trust my spin measurement, is what you are saying.
Yes, we do not.
Okay, so let me ask, so that was sort of jokingly, because I just thought to find an immediate application of the formula you have shown. But a different question that is a little more serious is, you said there is this independence of electron temperature, but I understand that is like to be expected if you measure at the same point, at the same radius, right? Because the dynamics do not depend on the electron temperature, just where the brightness is depending on where the. So, but does that mean that if you go to higher, to lower R-high, have hot disk electrons and the emission is moved to the larger radii, would that mean that you would expect a slower rotation to measure?
Yeah, so all I can tell you, Maciek, is that we see virtually no dependence on R high. It's sort of 10 to the minus 3 times.
Oh, wow. Okay, even for R high equal 1, where this emission seems to really be like far away in comparison to photon ring.
Okay, I wasn't going to show this because my.
Oh, but Charles, but exactly, you don't see because you measure at the same point. You don't see that because you measure at the same point. But if you are measuring at the place where the brightness leaves.
Okay, so the rotation might be different. Yeah, yeah, maybe. I don't have an answer. We haven't done that. But this,
thank you.
This shows the fit versus the measured value. So the colored is the predicted, and the gray is the measured in the simulation. And then this subtracts them. And you can see it really works well for the maths. And it doesn't work all that, or it doesn't work as well for the saints. And you may not be able to translate immediately in your head this model number into physics, but howls of outrage on the theory working group calls. So these are maths over here and saints over here, and then these are grouped according to spin, from negative spin to positive spin, and then grouped according to inclination and the smallest spins. So that feature that you see there is related to inclination. Okay, I've run over, which is unforgivable. Sorry.
Let's thank our speaker again. Yes.
Yeah.
Real great start to the season.
Fantastic.
Yeah.